Hello, everybody. So today I'd like to start presenting the company I work for, Johnson Electric. We are sort of quite a big company that probably nobody in this room has heard of. We make electric motors, and if you're good at math, you have already realized these are not big electric motors. They're rather small electric motors for many different applications. So you can see some of them here. And I would say you've probably never heard of Johnson Electric, but I'm pretty sure almost every one of you has used one of our products today. Most of what we do is in the automotive industry, and we make motors for pretty much anything that moves inside the car, except the actual motor itself in case of an electric vehicle. And we are a supplier to most of the OEMs around. On the other side, we have business in the industrial environment. So even if you don't own a car, if you own a printer, or if you took a coffee before, own a hair dryer, lawnmower, robot vacuum cleaner, etc., etc., I could go on. There's probably a Johnson Electric motor in there. The headquarters are in Hong Kong. It was founded in the 1960s, and about 15 years ago now, a little more, Johnson Electric acquired a company called Saya in Switzerland, in Morten, which is where I am based. So Morten is close to Bern. And this is now where the European headquarters are as well. So my role in the organization is I lead the digital transformation, and that is done from the European headquarters. So we are a mass production manufacturing company. As you might have realized, we produce about 3 billion motors a year, which means we have very low cycle times. We also, partially due to the requirements of the automotive industry, do 100% tests on all of our parts. So a lot of quality control, which is the topic I'm talking about today. And generally, we have very low defect rates. So even, of course, we don't want to send any faulty parts to the customer, but even before that, we have a very low scrap rate. So for most processes, that's below 1%. And that is important for the topic today. So where do we use machine learning today? Roughly speaking, we use machine learning in two areas. The first is image. So anything with vision AI, you can basically do quality control on anything that's visible, obviously. Then the problem or the biggest challenge is never to find a good AI system. There are many AI algorithms out of the box, very advanced deep learning algorithms available. Any teenager with a computer and Google Colab can do a vision AI. What the challenge is to actually obtain good quality data. So this is a very important part. You need to be very careful setting up your camera and lighting system. And then in our environment, one huge challenge is obtaining enough training data. This is usually very costly to get labeled data, and I'll come back to that in a second. So the second part is where we use AI is on time series. So there, the advantage is that data are much more readily available. We've seen various presentations already about IoT platforms. We now have sensors everywhere. Our production lines can record data on most of the assembly stations, if not all. And so having enough data is not the issue. Little or no calibration is needed on those data. We can usually do some post-processing quite easily on time series. But developing good machine learning algorithms is more of a challenge than with vision AI. That's not the topic of my presentation today. I just wanted to mention it, that we're also doing that. The topic of today is vision AI. So, as I mentioned before, the main challenge is the high cost of obtaining good ground truth samples, and not just defect. That's even more difficult because of the low defect rate, but even good parts, because if you want ground truth good parts, obviously you need to know that it's not a bad part, so you still need to do quality control on those parts. We have more of them, but we still need a reference. We need someone to label that and make sure that the ground truth is reliable. And by the way, as a small side note, of course, if you have someone label those data, and if you have it done during production, your AI is never going to beat your human manual quality control. It can only do just as well if the reference is the human. If you spend some more time really zooming in on the pictures and checking everything, you can get a better quality ground truth, or if you have a reference done by multiple people. But usually that obviously is more costly and more of a challenge. Then another challenge is that there are often unknown defect modes. So we're interested in detecting the defects that we know we have, but we're even more interested in detecting the defects that we don't know we have, right? Because those all of a sudden can cause quality problems, cause a spike in our scrap rate, or even worse, we can send bad parts to the customer. And finally, as I mentioned before, typically state-of-the-art AI systems are still very sensitive to changes in the conditions. Usually we immediately see it if someone changed the production process, because we all of a sudden reject all the good parts, basically. So to address some of these problems, Johnson Electric started a collaboration with a company called Cortica. They're a small company based in Israel, and they have developed a unique unsupervised AI vision technology. It can also be used for time series, but today, of course, the topic is vision. And together, a venture was created called Lean AI. So Cortica originally focused on several areas. Vision AI for automated driving was one of them. This Lean AI specifically focuses on industrial quality control. So Cortica's technology is a little bit different than what we know now and what everybody knows, the deep learning vision AI. Actually, it came even before the big deep learning revolution in around 2010 and the advent of GPU computing. It was based on earlier work on more biologically inspired neural networks. And the approach is a little more subtle. It's not as brute force. There are several steps involved. I won't go into detail, and partially I cannot go into detail because some of it is actually confidential, and I don't even know it personally. But the idea is that what the technology does, it extracts signatures based on images. And these signatures are then used to define higher level concept and the semantics. So based on that, what you can do is you can start reasoning and start getting things, putting things in context. Now, what that means is that in practice, you can use unsupervised learning once you've built the signature data set. And you can, it's also explainable. So unlike deep learning, you know why the system rejects or accepts a part. And you can then also easily transfer it to new tasks. So say you trained the system on a certain part with a certain defect, that knowledge about that type of defects is easily transferable to a next application. So back to my slide about the challenges we faced with using Vision AI. Those are addressed by Lean AI technology as follows. So Lean AI technology needs very few ground truth samples. And actually to set it up, initially, it doesn't even require any defect samples, just okay samples. And then once it's going, there is a part where it's sort of partially supervised, or we call it weakly supervised. You could call it reinforcement learning, however you want. There's a feedback loop built in to continuously improve the system. And at that point, it also can learn new defects. Because of this clustering of the signatures, it will learn defects, but it will also identify potentially new defects. Why is this important? Because regular deep learning AI, you could still say, okay, I don't need defect samples. I'm just going to do a one-class classifier on good samples, and then I can recognize good samples. If I can recognize good samples, I can also reject bad samples. That works if your good samples all look the same, which in our production at least is not the case. We have, for instance, a sintering process, and there's a lot of watermarks, there are smudges, every part looks different. So you really need to detect the defect, and you cannot just say, oh, if I know what a good part is, I can just accept only the good parts. That won't work. So that is important in this context. The Lean AI technology can identify these defects and learn the different defects modes, as well as identify potential new defect modes. And as I mentioned before, then the learned defects can be transferred to new applications. So very quickly, how this is look in practice. The algorithm is initiated with, in this example, 200 OK samples. It will really depend a little bit on the application. Then there's a stream of untagged data. So there you really don't need to do any annotation. It's just you can let your production line run and just feed into the system. The system runs in shadow mode. You don't actually use it yet. It's not ready. It's being trained, but by unsupervised learning. Then a new model is created, and that model can actually start being used in true production. But every now and then, the model is updated with new data, and batches are sent. The model selects itself images where it's not sure, and those images need to be hand selected or hand labeled, and then the system improves. But that is relatively few iterations are needed to get to a good quality. So what did we do with this technology up to now? We tried it on 2 production lines. One is a magnet production line in China, and the other one is powder metal parts. Those are actually parts for a gear train, for transmission in Canada. They're manufactured in Canada. So for the magnets, and they're very similar processes, so you'll see that the defects are similar, and we can test the transfer learning. So on the magnets, you can see already that the good part of the parts, so on the top here, it's only bad where it's marked in red. The rest of the part is also very irregular. So every part looks different, as I said before. We have different camera angles on this line, 10 cameras, showing the part from different angles, because we need to be able to detect defects on all the sides of the part, obviously. And there are many types of defects, I think 5 or 6 categories up to now. And 100% detection is required as usual, which, by the way, is always the discussion you have with the AI people, because in manufacturing we say, how many defects are acceptable, or how many false paths are acceptable, and you say 0, and they say, well, 0, you cannot validate 0. You have to do infinitely many tests. But the target is not to have any defects past the system. Let's put it that way. And everybody gets upset if one defect passes the system. But theoretically, you can do it for 5 years, and then one faulty part passes, and you're not at 100%. So, and also there's quite a bit of fluctuation in the lighting, even though we designed a new custom system. So in-house, we developed this system, this quality control system that you see here. This is a big setup with 2 hubs with cameras on it, 5 each. So the part goes on a conveyor belt, and in between it's flipped to get the same angles from the different side of the magnet. So we have 10 cameras in total, as I said. And up to now, we didn't achieve 100%, obviously, but it's about 99.9% and increasing. I guess 1 or 2 parts passed, and you cannot get rid of those anymore. So we'll asymptotically achieve 100%, hopefully. And the false alarm rates are quite low, lower than 2%, still working on that. 2% per camera means, of course, 20% total, right? Because every camera has 2% of its parts, the good parts that it will reject. So still some, you should depends on your business case, how expensive your parts are. You might still need to have some quality control of the rejected parts. I think an important thing to mention here is that is no longer quality control in the cycle time of the line, because that is a big pain point, right? These people are working in sync with the line. And if you go to these production lines, this is a person standing there sorting through these magnets. And I couldn't do that job. I'd be totally stressed out because the magnets just keep coming in and you just have to go just as fast or faster than the machine. You're constantly being chased by the machine. So that is no longer needed, but still some manual after work may be needed. We also tested knowledge transfer, this time between the different cameras, and we did observe that from one camera, once we trained one camera, the subsequent cameras can already get a quite good detection rate without any training. You can see this here. The second application were these rotors, so the powder metal rotors. I said it's a gear train before, but it's not. It's an oil pump, actually. This is quite a complex part with many different sides and angles. So we have a rotary table with a camera that takes a line scan camera that takes a 360 picture, and then we do some different angles as well. 8 cameras in total. The pictures are huge, by the way. I think the resolution is 8,000 by 1,000 or something. So that also, if you would do it with traditional deep learning, you would need huge computational power. That's also where the low compute solution of LineAI is quite useful. And they did try in the plant in Canada some commercial AI solutions, and they ran into these well-known issues. So with the LineAI technology, they were able to get similar figures as we saw in China. Here, even 100% detection of the test defects and less than 1% false alarm. And they initially, for these trials with commercial systems, they had to manually label 20,000 images. And now the LineAI technology could get it with 500 labeled images. Also, what they had to do with the previous system, they had to walk around with a big case of golden samples. So 100 samples that they knew the outcome of, and they had to run it through the line every week to make sure that to fine-tune the system. This is no longer needed either. So those are 2 applications I wanted to show you today. What are we working on right now to take this further? We are doing pilot tests to do further transfer learning, not just similar to the sintering process, but to other parts as well. The Catena X project was mentioned before. This is an example of federated data sharing. We are looking into the possibilities of using federated learning to work with other partners as well, outside companies, to create a backbone of systems. Because the huge problem is vision AI is really easy to do if your topic is available on the internet, but typically images of parts from manufacturing are not available on the internet. So we need to find a way to create this large scale model effect that you have now with generative AI as well. I dabbled a little bit with DAL-E to try to generate fake images of faulty parts. But it's very good at showing an astronaut in space smoking a cigar, but it's not very good at creating an image of a magnet with a crack, basically. And then an interesting avenue we're exploring, and I saw there's a talk about using digital twins in conjunction with AI later, so I'm very interested in hearing about that. We want to use linear technology in conjunction with our digital twin technology to do predictive testing, basically. So this time on time series, we identify a digital twin as fast as possible, and we can stop tests early, especially endurance tests that sometimes can take up to months. This is an interesting avenue. And then, as I mentioned before, use of generative AI for enhancement of our training data sets. But there we run into these problems of simply there's not enough training data available. For Lean AI, they are working on mainly metal surface inspection at the moment. So the two examples I showed before, and they're exploring some further applications in this area because, of course, they already have a backbone trained on this type of data. And then the next step will be to explore other verticals like plastics injection or electronics, and even venture into time series data. And go into analytics and insights. So that's what I had for today. Thank you very much for your attention. And I think there's some time for questions even.